Welcome to the Empire of Dirt. Today we got a little project, but it's going to have a little bit of complication to it. I machined these throttle bodies, or injector bodies, really what they are. I made them in 3 pieces. I machined up each into 2 individual bodies, and then I machined a flange plate to join them, and I welded them on the inside. So first thing that I need to do is to clean up those welds, so I'll use that. I'll index them. I'll index these on the mill, and then I'll run a boring bar down through them to clean them out, and that's a fairly easy project. The more complicated one is I need to bore the holes, the openings for the fuel injector bodies. And that's going to be a little harder because, as you can see, they're at an angle. So I'm going to have to figure out some way of holding them so that our line where the bore is going to go in is going to be in line with the axially in line with our mill. So that means they're going to be mounted at an angle, and I'm going to drill and bore those so that they're going to be straight. So that's going to be a little harder to do. So first thing, we need to put them in the mill and index them to get our positioning. When you do this, you want these things in here. You want them in the vise tight and square. And what happens, because you've got one jaw that is stationary and you have one jaw that is moving back and forth, this jaw tends to have play in it. And traditional old style vices, this jaw completely floated, and they're really hard to get everything in there tight, because every time you push, it tilts up and wants to tilt the whatever you're holding, it tries to tilt it up. The Kurt vices, which are very, very nice vices, I think it was them that invented this style of vice, which has I guess it's got an inclined surface inside, so as it pushes, it also pulls it down. This is just a cheap Chinese copy. It doesn't work as nice as a Kurt. So there's still some lifting, and you can see as I lift, this parallel stays nice and tight, this one gets loose. So you have to tighten it a little bit, tap it down, there it's loose again, tap it down, tighten it, there it's loose again, tighten it, it's tight again. So it's a little process of tightening things down and tapping things down to get them in there nice and tight and keep them straight. So we're set up here with a rotary dial indicator, and you may not be able to see this. I'll take it off and give you a close-up of it. But what happens is, as this thing spins, you'll see run out on the dial, and as you manipulate the axis, the X and Y axis, you'll see that run out go down, down, down until it's virtually non-existent, and then you know that it's centered. So you can see the run out on that, and as I jog one way or the other, it either gets worse or better. So there we're getting better by jogging the y-axis, and there you can actually just see it jumping, which means we've got past. So there we go. So right now there I was jogging at 5 thou increments, and if I change that to 1 thou increments, I might be able to get it better. And that's, so there we are, that's about as good as we're going to get it. That's plus or minus. It's oscillating back and forth about half a thou in each direction. So we're within a half a thou of the center, which is more than adequate for what we're going to be doing here. So we've got the boring bar mounted in the mill now, and all we're doing right now, you know, I've been cleaning it up, so we're down to cleanups, and I'm down to taking 10 thou on the radius per cut. So all we do is just turn on the head. Nope, bad glare. We've just really got two commands, one of them telling it to go down in the Z to 0.4, and then once it's there we tell it to come back up again to 0.05, and that's all it's doing. It's just going down and coming back up. So there's our cleaned up bores, so no problem, that was easy enough to do. The next part, figuring out how I'm going to hold those exactly, that's going to be a little tougher, so we'll see how that goes. This is what I came up with for holding these manifolds, and I 3D printed this part as a base, a mount. So I drilled, or I printed holes, and then I tapped them for threads, and those ones I just went right through with bolts. And I put these holes in this face. They go right through, and so when you print, you know, there's a wall all the way around that hole. So when I clamp this in the vise, those guys are going to be all going to be in compression, so I'm hoping that's going to be enough material that I can clamp that thing down fairly solid. And you can see now that my ports that I need to drill and bore are in line with the axis of the mill. I wouldn't want to do any actual milling, I don't think, with a system like this where you're imparting a lot of side loads. But drilling, the majority of your load is axial, in line with the axis of the mill, or of the drilling head. There is some torque because you are resisting. The part's resisting the turning of the bit, but I think this is going to be plenty rigid enough if we go real slow and just don't get out of hand. So I guess time will tell. And again, we've only got 4 of them to do, so as long as I don't crack this piece somehow, I think it's going to work okay. It was about 9 hours to print that out of PTEG or PETG, whatever, I can't remember which pronunciation it is, but I'm hoping this is going to work. This is an edge finder, and what I need to do is I need to position the milling head over the center of my bore, and how I determine that is this is an edge finder. I'll find this edge, I'll find the edge on the other side of the body, and I'll note those dimensions on my screen from my CNC, and I'll divide them by 2. That'll give me the center line in the y-axis. Then I'm going to go down and I'm going to find this sharp edge at the bottom of the body here, and I know from the computer, from my CAD system, I know how far in the x axis my center line is from that edge. So how these things work is they're on a spring system, so the bottom portion is free to move around, and you spin the motor, and these things are off center, so it's eccentric, it's running out of time or out of axial alignment with the center, and as you bump it up against the object you're trying to detect, that axial alignment becomes less and less and less and less and less, and then it will run absolutely perfect, and then you move it 1 more thousandth of an inch, and the friction of the outer portion up against the part will cause it to run back out of alignment again, and you'll see it bump over, and then you're within 1,000th of an inch of the edge, and you can't get much better than that. So we'll just go ahead and index these parts. I don't know if you can see it, but it's getting closer and closer. And right there, it moved off. And this one actually makes a noise when it does. So that's one edge. That tip is 0.2 of an inch in diameter, so once we find that edge, we jog it over by 0.1. Now that's our 0. I don't know if you can hear it, but there's our other point. I've got a pilot, what's called a pilot drill in here now. We found our center, our 0, We've got a pilot drill in here, and what a pilot drill is it's got a bigger shank, and then it's got a very small tip on the end. Drills, they tend to wander, especially starting, and that's typically why you center punch. You put a center punch where you want to start. If you're manually drilling it, it centers that drill bit. But most drill bits, especially small ones, are very flexible too, and they'll find their own center if you're not careful. So with a pilot drill like this, it's very stiff. And when you're using a milling machine, or to some extent even a drill press, you can get away without center punching. And I'm using a very light feed because, again, I don't want to overpower that plastic holder. So we've switched to a 1/4 inch drill bit, and we'll drill a 1/4 inch pilot hole, and that, again, just there's less pressure using a smaller drill bit, less likely to dislodge that fixture. and then the next after that we'll drill it out to its proper 10mm size. And that's called peck drilling, where it's only drilling, I had it set there to only drill 0.1 or 100th of an inch per peck. And what that does is every time the drill bit comes up, it clears the chips out of the hole. When you're drilling small diameter holes like that, especially in aluminum, you can pack up the drill bit with drillings with chips to the point where you just jam the whole thing up and break a bit. So there's our finished hole. So it's got a main center bore of 10mm and then I guess a counter bore of 0.55 inches, and then we chamfered the edge, and we had to provide a little bit of relief around the outside edge too. So it was a multi-step process. I didn't show all the steps because it's just basically the same thing over and over again with different tools. But I'll show you all the different tools that were required to finish this. And this shows you the selection of tools that were required to do all these operations. The indexer to find our positions, our pilot drill, our 1/4 inch drill that we drilled a through pilot hole, then a 10mm drill. Then I used a 1/2 inch end mill to bore a straight hole that gave me a flat bottom that I needed. Then the boring head, I took that 0.5 hole out to 0.55, and then we broke the edges on the hole with the chamfer tool. So quite a long process. I didn't show you all the operations because it's just changing tools, and it took quite a while. It took me like an hour to do one hole. So it's going to be half the day probably, basically doing 4 holes. But that's the way it goes.